Hello and welcome to another episode of IT for Non-Techie. In today's episode, we are going to talk about networking. No, not this type of networking, the interesting type of networking. So, if you are working with software development teams or infrastructure teams, or even if you are preparing for any cloud certification, this video could be useful for you because it will cover the basics of networking. You will discover what are the different types of network, what is IP, what is TCP, the different protocols, what is NIC, NAT, CDNs, and so on. A lot of interesting stuff. And as usual, don't hesitate to like the video and subscribe to the channel. And if you have any request or comment or anything, you can leave a comment on this video. Also, you can reach out to me through my social media accounts. You will find them in the description. So with that being said, I will let you watch the video and enjoy your learning. Now, let's start with some definitions. First of all, let's start with network. What is a network? At its core, a network is simply an interconnected system of devices, also known as nodes, that communicate and exchange data. These devices can be anything from your smartphone and laptop to servers and even smart home gadgets. The primary goal of a network is to ensure seamless data transmission and resource sharing, making it easy for information to move smoothly from one device to another. But you may ask, those devices are so different, how they can communicate together? That's where protocols come in. A protocol is like a universal language that all devices understand, regardless of their type or brand. It sets the rules and guidelines for how data should be transmitted across the network to ensure everything works smoothly. Similar to grammar, like how you should formulate a sentence, protocol does the same thing. Protocols handle several crucial tasks to keep data flowing correctly. First, they break down data into smaller, manageable parts for efficient transmission. These are called data packets. For example, when you send a photo, it doesn't travel as one large file. Instead, it splits into smaller chunks, which are then reassembled at the destination. Second, protocols ensure device identification. Just like every house has a unique address, each device has a unique identifier, such as IP address or MAC address, to make sure that the data reaches the right destination, like how it will know that it should go to that server specifically. It identifies that server by its IP address or its MAC address. Lastly, protocols are responsible for error detection and correction. Think of this like spell check for data. If something goes wrong during transmission, protocols detect the issue and correct it to maintain data integrity. One famous protocol out there is the TCP/IP, which stands for Transmission Control Protocol, Internet Protocol. It's the backbone of the internet and most private network. Without TCP/IP, you won't be even able to watch this video. So everyday activities like sending emails, streaming videos, or loading a simple web page won't be possible without it. It ensures that data gets where it needs to go reliably and securely. Since we now know the definition of network and we know a little bit about the protocols, let's move to the different types of network. You are at home and your laptop, phone, smart TV, even your smart fridge are all connected to the same Wi-Fi. That's what we call a LAN, a local area network. It's just a way to connect devices within a small area like your home, an office, or a school, so they can share stuff like files, printers, and the internet. What's so cool about LANs? They are super fast. Plus, they are usually controlled by one person or organization, which makes it easier to keep things secure. You can have a LAN that's wired to Ethernet cables for stability or wireless with Wi-Fi for more flexibility. Now, imagine you are in Paris, sending an email to a colleague in New York. That email doesn't just leap across the ocean magically. It travels through a WAN, wide area network. A WAN connects multiple LANs, local area networks, across large distance, whether it's between cities, countries, or even continents. In fact, the internet itself, the most obvious example, It's the largest one in the world, linking millions of networks globally. What makes a WAN stand out is its ability to cover a vast area. Unlike a LAN, which is limited to a home, office, or school, a WAN stretches across regions and sometimes worldwide. Because data has to travel such a long distance, WANs are usually slower than LAN. This isn't because the technology is outdated, it's simply due to the complexities of routing data over thousands of miles through different networks and infrastructure. And speaking of infrastructure, WANs rely on a big player like leased telecommunication lines, satellites, and fiber optic cables to keep data flowing. And since they cover such extensive areas, WANs aren't managed by just one organization. Instead, they often controlled by multiple service providers, governments, and companies working together to maintain the network. For a live example, think of a multinational corporation connecting its offices in New York, Tokyo, and London, all through a WAN. Or the most obvious example, the internet itself, which links people, businesses, and devices from every corner of the globe. Now, every time you watch a video or you hop on a Zoom or a Teams call, that's the power of the WAN. Now, imagine a network that connects an entire city, linking government offices, businesses, schools, and even public Wi-Fi hotspots. That's exactly what a MAN is, a metropolitan area network. It's designed to cover a large geographic area, typically the size of a city or a large campus, connecting multiple LANs within that region. The main purpose of a MAN is to provide high-speed connectivity across the city. It allows for efficient communication between organizations, government offices, and even residential neighborhoods. Whether it's transferring data between corporate offices or providing public Wi-Fi in parks and cafes, a MAN ensures fast and reliable connection within a metropolitan area. What makes a MAN unique? It covers a space larger than a LAN but smaller than a WAN. To handle the demand for speed and reliability, MANs often use fiber optic cables for high-speed data transmission. And like home networks, MANs are usually managed by Internet Service Providers, ESP, or large organizations ensuring professional maintenance and security. Oh, wait a second, let me connect my AirPods to my phone. That simple connection is the PAN, the Personal Area Network. A PAN is a small network designed to connect your personal devices within a short range, typically just few meters around you. It's all about creating seamless connections between the gadgets you use daily. The main purpose of a PAN is convenience. It helps you easily connect devices like smartphones, tablets, laptops, and Bluetooth accessories for personal use. Whether you are sharing files between your phone and laptop, syncing your smartwatch with your phone, or connecting a wireless mouse to your laptop, that's a PAN quietly working in the background. What sets PAN apart is its short-range capability, usually within 10 meters. It relies on wireless technologies like Bluetooth, infrared, and even USB connections for wired options. Now, this image represents the summary of the different types of networks out there. So I hope it was clear for you, because now we are about to shift gears and get into more interesting and deeper things about network. Let's first understand that networks don't just magically connect on their own. They rely on specific devices that handle data flow, manage connections, and ensure everything runs efficiently and effectively. One of the most important devices you likely use every day without even realizing its significance is the router. A router is essentially the brain of your network, responsible for connecting different networks together and making smart decisions about where data should go. Its main job is to ensure that data packets, the small chunks of information, reach the correct destination quickly and efficiently. Think of it like traffic controller, guiding data through the fastest and safest road to avoid the congestions and delays. More like, the way we use Google Maps or Waze. it selects the fastest way and the safest way for you. That's the same thing. One of the key functions of a router is routing. This involves determining the most efficient path for data to travel. The router examines the destination IP address of each data packet and decides the best route to get it from the sender to the receiver. This isn't just a fixed process. Routers constantly adjust the path based on the current network conditions, such as traffic load or outages, to maintain optimal performance. Another important function is the NAT, the Network Address Translation. NAT allows multiple devices on a local network to share one single public IP address when accessing the internet. It translates private IP addresses used within your home or office into a public IP address when sending data out, and then it translates the incoming data back to the correct private IP address. This not only conserves IP addresses, but also adds a layer of security by masking internal network details from outside world. In addition to routing and NAT, many routers come with built-in firewall capabilities. This means they can filter incoming and outgoing data, blocking suspicious activities and protecting your network from unauthorized access. Think of it as a security guard that monitors network traffic, allowing only safe data to pass through. So, how does all of this work in real life? Let's say you open a website on your phone. Your device sends a request, which the router receives. The router then checks where the request needs to go and forwards it to the correct destination on the internet. Once the website data comes back to the router, ensures it gets delivered to the right device on your network. This entire process happens in milliseconds, working silently behind the scenes. Now that we've covered the role of the routers in managing data flow between networks, let's talk about another essential device that works within a local network: the switch. While a router connects different networks, a switch focuses on connecting devices within the same network, like computers, printers, and servers, in an office or a data center. A switch plays a critical role in managing the flow of data between these devices. Think of it as a skilled traffic director, ensuring that data packets reach their exact destination. So, a switch is unlike a hub which blindly sends data to all devices on the network. A switch is much smarter than that. It sends data only to the intended recipient, which helps improve efficiency and reduce unnecessary traffic. Switches operate at layer 2. Now we are going to talk about OSI Model, but don't worry, we are going to explain the OSI Model in detail later on. So just capture this information and move on. So switches operate at layer 2, also known as data link layer of the OSI model. They rely on MAC addresses. The MAC addresses are unique identifiers assigned to each device. They use these MAC addresses to address and direct the network traffic precisely to that device. When a switch receives a data packet, it checks the MAC address to determine which device the data is meant for and sends it there directly. This targeted delivery not only speeds up communication but also helps reduce network congestion. To put this into perspective, imagine a data center with thousands of servers handling different tasks such as managing databases, running applications, or storing files. When a client sends a request for specific data, the switch doesn't flood the entire network with this request. Instead, it efficiently directs the request to the exact server that holds the needed data. This precise routing reduces network traffic, lowers latency, and ensures a smooth, high-performance operation, even with a massive number of devices connected. In short, a switch keeps your local network running efficiently, ensuring data gets where it needs to go quickly and without unnecessary detours. Let's move on to another key device that keeps us connected in today's wireless world, the access point. If you ever connected your phone or laptop to a Wi-Fi at a cafe, airport, or even in your own home, you've interacted with an access point, probably without even realizing that. An access point is a device that allows wireless devices like laptops, smartphones, and tablets to connect to a wired network using Wi-Fi. Think of it as a gateway between the wired infrastructure and the wireless devices. While a router connects a network, an access point extends the router's capabilities, enabling devices to communicate wirelessly within the network. One of the key functions of an access point is to act as a network bridge. It connects wired and wireless networks, allowing data to flow seamlessly between devices that rely on cables and those that operate wirelessly. This makes it easier to integrate wireless devices into traditional network without needing additional cables. Another important role of an access point is coverage extension. In larger spaces like offices, hotels, or even big homes, a single Wi-Fi signal might not cover every corner. Access points help solve this by expanding the reach of the wireless network, eliminating dead zones, and ensuring strong connectivity throughout the area. Additionally, the access points are designed for device management. They handle multiple wireless connections simultaneously, ensuring each device has a stable and secure access to the network. Router and modems, for me, is the same thing, but actually it's not the same thing. So now we are going to talk about the modem. So if you ever wondered how your home network connects to the wider internet, the modem is the unsung hero making that possible. A modem serves as the gateway between your local network and the internet service provider, the ESP. Its main job is to convert digital data from your device into signals that can travel over the ESP infrastructure like the DSL, the cable, or the fiber optic lines. Then it does the reverse, converting those signals back into the digital data that your devices can understand. This is where the name modem comes from, short for modulator and demodulator. One of the modem's key functions is modulation and demodulation. This process transforms digital signals used by your device into analog signals suitable for transmission over traditional communication lines, and then back again when the data is received. Without this conversion process, your devices won't be able to communicate with the internet. The modem also acts as a network bridge connecting your router to the ESP. While the router manages traffic within your local network, the modem ensures that data can flow in and out of your network, giving all your devices access to the internet. Another essential role of the modem is signal conversion. It helps data formats to ensure smooth communication between your local network and the ESP system. This compatibility is critical for maintaining a stable and reliable internet connection. So I know a lot of information, but let's bring them together in just one simple example to understand everything. So let's take the example of sending an email, how the data flows. So your laptop connects to the access point via the Wi-Fi. This is the wireless connection. That access points will send your email to the switch, and then the switch will forward it to the router. The router processes the data and sends it to the modem, and then the modem sends that data to the internet. When the email's response comes back, the process is simply reversed, flowing from the internet to the modem and then to the router, the switch, the access points, and then to your laptop. So that's the summary of the data flow, and that's how all the devices are used in order. Now we are going to talk about security. So let's shift our focus to an equally important component of network, which is security. the firewalls. While the previous devices are responsible for connecting and directing data, a firewall's role is to protect the data and your network from potential threats. A firewall acts as a security barrier between your trusted internal network and untrusted external networks, such as the internet. Think of it like a security guard standing at the entrance of a building, checking credentials before allowing anyone inside. It controls the flow of network traffic based on predefined security rules, determining which data packets are safe to pass through and which should be blocked. One of the core functions of a firewall is packet filtering. It inspects individual data packets, small chunks of information traveling across the network, and decides whether to allow or block them based on specific rules. For example, it might block packets from suspicious IP addresses or allow any certain type of traffic like emails or secure web browsing. Another important function is stateful inspection. Unlike basic packet filtering, stateful inspection doesn't just look at individual packets in isolation. Instead, it tracks the state of active connections, making sure that incoming data is part of a legitimate established communication session. This adds an extra layer of protection by identifying and blocking malicious attempts to distribute or hijack connections. Firewalls can also perform application layer filtering, which monitors data related to specific application. This allows network administrators to control activities like blocking access to certain websites, restricting the use of specific apps, or even filtering out harmful content. It's like having a content moderator for your network, ensuring only approved data and applications are accessible. There are two main types of firewalls. Network firewalls, which are designed to protect entire networks, often installed on routers or dedicated security devices. They are commonly used in businesses to secure large-scale networks. On the other hand, there is host-based firewalls, which are installed on individual devices such as laptops, smartphones, or servers. These provide an extra layer of defense, protecting devices even when they are outside the main network, like when you are using public Wi-Fi. In summary, a firewall is your network first line of defense, actively monitoring, filtering, and controlling data to keep unwanted threats out while allowing safe traffic through. Now that we've explored the role of firewalls in the network security, let's dive deeper into two primary types, stateful and stateless firewalls. These firewalls function differently, each offering unique advantage depending on the network security needs. Let's start with the stateful firewall. Stateful firewall is like a security guard who doesn't just check IDs at the door, but also keeps a track of who's already inside. It monitors the state of active connections, meaning it doesn't just filter individual data packets, it understands the context of the traffic. This allows the firewall to recognize whether incoming data is part of an existing legitimate connection or if it's from a new potentially suspicious source. Because it tracks those ongoing sessions, stateful firewalls provide the strongest security compared to the stateless one. They are commonly used in corporate networks, especially to monitor secure connections like VPNs, where maintaining the integrity of active session is so important. On the other hand, a stateless firewall operates more like a guard who checks each person entering without remembering who passed through earlier. It filters traffic based solely on predefined rules, without considering whether the data belongs to an existing connection. This makes stateless firewalls faster and simpler to manage, but also less secure, because they can detect suspicious patterns or attacks that unfold over multiple packets. They are ideal for simple networks with a pre-detectable traffic, such as basic firewall setup in small home router. So how do firewalls actually work? Let's break it down step by step. First, when data packets arrive, whether incoming or outgoing, the firewall inspects them. Each packet contains key information like the source IP address indicating where it's coming from, the destination IP address where it's going, the port number specifying which service or application it's targeting, and the protocol used such as TCP or UDP. Next, the firewall inspects the packet, analyzing these details to determine if it's aligned with the network security policies. It checks whether the packet comes from a trusted IP address, whether it's targeting a load port, or if it follows the correct protocol. After inspection, the firewall applies its security rules. If the packet matches an allow rule, it passes through to its destination. However, if it matches a deny rule, the packet is blocked, preventing potential threats from accessing the network. In addition to blocking or allowing traffic, many firewalls also perform logging and alerting function. Suspicious or blocked traffic is often logged for further security analysis, allowing network administrators to review and investigate potential threats. Some advanced firewalls can even trigger real-time alerts to notify security teams of high-risk activities, enabling swift responses to security breaches. To ensure that firewalls are effective as possible, it's important to follow some best practices. First, define clear security policies. Know exactly what traffic should be allowed and what should be blocked based on your organization's needs. Applying the least privilege principle is key. Only allow traffic that is absolutely necessary and block everything else by default to minimize vulnerabilities. It's also crucial to perform regular updates on firewall firmware and software to patch any security vulnerabilities. Cyber threats evolve rapidly, so keeping security tools current is essential. Additionally, monitoring logs regularly can help detect patterns of suspicious activities that might indicate a security issue before it escalates. Lastly, consider implementing multi-layered security. A firewall alone isn't enough for comprehensive protection. Combining it with antivirus software, intrusion detection, and the preventing system and VPN creates more robust defense against threats. By understanding how both stateful and stateless firewalls work and following these best practices, you can strengthen your network defenses and ensure more secure data flow across your systems. As we continue to explore the landscape of network security, it's important to look beyond the basic devices like firewalls, routers, and switches. While these components are essential for managing and directing traffic, modern networks require advanced security measures to safeguard data against increasingly sophisticated threats. That's where technologies like VPN, virtual private networks, and IDS, EPS, intrusion detection and prevention systems come into play. These tools are designed not just to control traffic, but also to enhance the privacy, secure remote access, and proactively detect and prevent cyber threats, adding critical layers of defense to any network environment. Starting with VPNs, or virtual private networks. These are powerful tools designed to create secure, encrypted tunnel over the internet. When we say encrypted, see it like you and your friend, you have a topic that you want to talk about, but you don't want the people around you to understand you. So you start using codes to understand each other. So only you and him can understand that code, the others, they don't. This is what encryption is, but it's more complicated than that. Its primary purpose is to protect your data from interception, ensuring that sensitive information stays secure, even on public networks. VPNs also help maintain anonymity online by masking your IP address, making it difficult for third parties to track your online activities or identify your location. Additionally, VPNs are invaluable for remote access. For example, employees working from home can securely connect to their company's internal network through a VPN, accessing files and resources as if they were in the office, all while keeping the data encrypted and protected from external threats. Now, moving to IDS, EPS, which is Intrusion Detection System and Intrusion Prevention System. These technologies are the vigilant eyes and active defense mechanism of network security. An IDS function like a security camera. It monitors network traffic for suspicious activities, such as unauthorized access attempts or signs of malware, and generates alerts to notify the security teams. However, it's a passive system, meaning it detects potential threats but doesn't take action to stop them. Its job is to provide visibility into network activity so that administrators can investigate and respond accordingly. In contrast, an EPS, which is Intrusion Prevention System, is more like a security guard who not only detects suspicious activity but also intervenes in real time to stop it. An EPS actively analyzes network traffic, identifies threats, and automatically blocks malicious activities, such as preventing harmful data packets from entering the network or blocking IP addresses associated with known attacks. This proactive approach helps prevent security breaches before they cause any damage. Both EDS and EPS rely on two main detection techniques: signature-based detection. Signature-based detection identifies known threats by comparing network traffic to a database of known attack patterns, much like how antivirus software detects viruses. While this method is fast and effective for familiar threats, it may miss new and evolving attacks. To address this, anomaly-based detection comes into play. It monitors for the unusual network behavior that deviates from the norm, such as unexpected data transfers or strange login pattern. This technique is crucial for identifying new or unknown threats that haven't been documented yet. To put this in perspective, imagine the security setup of a building. The ADS is the surveillance camera. It keeps watch, records activity, and alerts you if something seems off. The APS, on the other hand, it's like the security guard who sees the suspicious activity and immediately steps in to stop the intruder from gaining access. In a network environment, ADS-CPS systems work similarly to detect and prevent cyber threats like hacking attempts, malware infection, and potential data breaches. In summary, while VPNs provide secure encrypted connection that protect data privacy and enable safe remote access, ADS-EPS systems focus on detecting and responding to security threats in real time. Together, they form a robust defense strategy, ensuring both secure communication channels and proactive protection against cyber threats. As we learn more about networking, it's important to understand the hidden technologies that keep everything connected. While devices like the devices we've seen earlier, the routers, the switches, and so on, they handle the movement of data, tools like DNS, DHCP, IP addresses, NAT, MAC addresses, NICs, and virtual network interfaces, they work quietly in the back. Now let's start with DNS. Domain Name System. Think of it as the internet's phone book. It translates easy to remember and readable domain names like www.google.com into numerical IP addresses, which computers use to locate and communicate with each other. Without DNS, we'd have to memorize long strings of numbers for every website we visit. One of its key functions is name resolution, which converts human-readable domain names into machine-readable IP addresses. Additionally, DNS uses caching to store previously resolved queries locally, which speeds up future requests and reduces website load times. For example, when you type www.google.com into your browser, DNS quickly finds the corresponding IP address, allowing the website to load almost instantly. Next, we have DHCP, Dynamic Host Configuration Protocol, which plays a crucial role in managing IP addresses. Imagine manually assigning an IP address to every device you connect to Wi-Fi. It would be a hassle. Thankfully, DHCP automatically assigns IP addresses to other network configuration details like subnet masks and default gateways to devices on a network. This process eliminates the need for manual IP configuration. DHCP also uses something called lease time, which means IP addresses are assigned temporarily and get removed periodically. For instance, when you connect your phone to a Wi-Fi, DHCP assigns it an IP address automatically without you having to lift a finger. Speaking of IP addresses, an IP address is a unique identifier assigned to each device on a network, allowing them to communicate effectively. There are two main types of IPs, IPv4 and IPv6. IPv4 uses 32-byte address format like 192.168.1.1, providing around 4.3 billion unique addresses, a number that's almost exhausted due to the growing number of connected devices. To address this limitation, we have IPv6, which uses 128-byte address formats such as 2001 2.t, offering a virtually limited number of IP addresses. This ensures the future scalability of internet-connected devices. Moving on to NAT, Network Address Translation. This technology allows multiple devices on a private network to share a single public IP address when accessing the internet. NAT serves two primary functions: IP address conservation and security. It helps reduce the need for unique public IP address, which are limited resources, and adds a layer of security by hiding internal IP addresses from external networks. A common real-life example of a NAT is your home network. All devices, laptop, phones, smart TVs, and so on, they connect to the internet using the same public IP address, while internally, they have different private IP addresses. Now let's talk about MAC addresses, Media Access Control Addresses. A MAC address is a unique identifier assigned to a network interface used for communication at the data link layer, layer 2 of the OSI model. Think of it like a car's license plate. Each vehicle has a unique number, just like each device on a network has a unique MAC address. This helps devices identify and communicate with each other within the same local network. Closely related to MAC addresses is the NIC, Network Interface Card. An NIC is a hardware component that allows a device to connect to a network, whether via a cable or via the Wi-Fi wireless. Its key functions include managing physical connections and handling data transmission to and from the device. Without the NIC, your device wouldn't be able to connect to any network at all. Lastly, we have the concept of a virtual network interface, which is especially important in the world of cloud computing and virtualization. And like the traditional NIC that relies on physical hardware, virtual network interfaces allow virtual machines and cloud instances to connect to networks without any physical components. For example, in platforms like AWS or Azure, servers use virtual interfaces to connect to private or public networks seamlessly. We spoke earlier about the OSI model, just fragments of information. Now we are going to talk about the OSI model in details. It sounds fancy, right? So let's start. OSI model is Open System Interconnection Model, which serves as a universal framework for how data moves across networks. Think of it as a blueprint that explains how devices, applications, and systems from different vendors can communicate with each other seamlessly. The OSI model helps standardize network communication, ensuring that everything from your smartphone to complex servers can work together without compatibility issues. What is the purpose of the OSI model, you may ask? The purpose of the OSI model goes beyond just standardization. It helps simplify network troubleshooting, making it easier to identify and fix issues by isolating problems within specific layers. It also guides network designs and development, providing a clear structure for building efficient, scalable networks. Additionally, the model promotes vendor-neutral networking, allowing devices from different manufacturers to work together without conflict. From a security standpoint, it helps enhance network protection by addressing vulnerabilities at each layer. The OSI model also supports protocol flexibility, making it easier to implement updates or changes. Lastly, it simplifies complex networking concepts, making them more accessible for both beginners and IT professionals. The OSI model is divided into 7 layers, each with distinct roles and responsibility that contributes to the overall process of data communication. Starting at the bottom, we have the physical layer, layer 1. This layer is responsible for the physical transmission of raw data, as electrical signals, light pulses, or radio waves. It defines the hardware involved in this process, such as cables, switches, network cards, or even Wi-Fi signals. For example, when data travels through the Ethernet cable or over fiber optics, this is the physical layer handling that transmission. Next is the data link layer, layer 2, which manages communication between devices on the same local network. It packages data into frames for transmission, handles error detection, and uses MAC addresses to identify devices. A protocol like Ethernet and Wi-Fi operates at this level. A common real-life example is when you connect your laptop to your home router via Wi-Fi. This connection is managed at layer 2. Moving up, the network layer, layer 3, focuses on routing data between networks. It determines the best path for data to travel from the source to the destination, relying heavily on IP addresses. Protocols like IP and ECMP function here. When you send an email, the data is routed through various networks, with layer 3 deciding the most efficient path. The transport layer, layer 4. It ensures reliable data transmission between devices. It's responsible for error detection, data segmentation, and flow control. 2 key protocols work at this layer, TCP and UDP. For example, when you send an email, TCP guarantees that the message arrives intact, even if it's broken into smaller data packets during the transmission. The session layer, layer 5, it manages communication sessions between devices. It establishes, maintains, and terminates sessions, ensuring continuous data flow during activities like video call or online transactions. For instance, when you stay logged into an online shopping site while browsing multiple pages, the session layer maintains that connection in the background. The presentation layer, layer 6. It acts as the network translator. It converts data into formats that application can understand, handles encryption and decryption for security, and manages data compression to improve efficiency. A common example is the SSL/TLS encryption, which ensures your data when you access websites via HTTPS. Finally, the application layer, layer 7, is the layer that directly interacts with the user. It provides network services like email, file transfers, and web browsing through applications such as browsers, email client, and messaging apps. When you open a website in Chrome or Firefox, you are engaging with the application layer, which facilitates your connection to web servers and manages the data you send and receive. In summary, the OSI model breaks down the complex process of network communication into 7 manageable layers, each playing a vital role. From the physical transmission of data to the user-facing application, every layer contributes to the seamless, secure, and efficient flow of information. Understanding these layers is key not only to troubleshoot network issues, but also for designing robust and secure networks and gaining a deeper insight into how the internet works. Now, let's pay some attention to the protocols, the network language. It's crucial to understand the role of network protocols. These are the rules and standards that define how devices communicate with each other over a network. Without these protocols, devices like computers, smartphones, servers, and routers wouldn't be able to exchange information effectively. In simple terms, think of a network protocol as the language that devices use to talk to each other. Just like humans need a common language to communicate, devices rely on these protocols to ensure data is sent, received, and understood correctly. At the heart of a network communication is the TCP/IP, which serves as the foundational set of protocols used to connect devices on the internet and private networks. TCP/IP defines how data should be packaged, addressed, transmitted, routed, and received. TCP, which is Transmission Control Protocols, it ensures that data is delivered accurately and in the correct order, establishing a reliable connection between the sender and the receiver. On the other hand, IP, which is the Internet Protocol, handles the addressing and routing of data packets, ensuring they reach the correct destination. To put this into perspective, think of TCP as the email carrier who ensures your package arrives intact, while IP acts as the address label that tells the carrier where to deliver it. Moving up the layers, we reach the application layer where user interaction happens. This layer allows application to communicate over the network using specific protocols. For instance, HTTP, which is Hypertext Transfer Protocol, powers websites, transferring web pages from servers to browsers, while HTTPS, which is Secure HTTP, adds encryption for secure online transactions. FTP, which is the File Transfer Protocol, is used to transferring files between computers. And SMTP, Simple Mail Transfer Protocol, handles sending emails. While it comes to receiving emails, protocols like POP3, which downloads emails to your devices, and EMAP, which sync email across devices, come into play. Another key protocol is the DNS, which we already discovered earlier. We already know what DNS is, the domain name system, which translates user-friendly domain names like google.com into IP addresses, helping browsers find the correct servers. To make all this communication possible, network ports play a critical role. A port in networking is like a virtual door that directs network traffic to the right application or service on a device. Imagine your computer as an apartment building. The IP address is the building address, identifying the device on the network, while the port number is the apartment number, indicating which specific application the data should go to. Without ports, Your device wouldn't know whether incoming data is meant for your web browser, email client, video game, or file sharing app. Now, how do those parts work? When data travels over the internet, it's broken into small chunks called packets. Each packet includes the source IP address, the destination IP address, a source port identifying the application sending the data, and a destination port identifying the application meant to receive the data. When the data reaches your device, the IP address ensures it arrives at the correct destination, and the port number directs it to the right application, whether that's your browser, email client, or another service. Next, we have the transport layer, which ensures data reliability and manages the flow of data across networks. TCP, Transmission Control Protocol, is a reliable connection-based protocol used for tasks like web browsing and email. It ensures that data arrives in the correct order without errors. In contrast, UDP, User Datagram Protocol, is a faster, connectionless protocol, ideal for real-time applications like video streaming and online gaming, where speed is more critical than perfect accuracy. The internet layer handles addressing and routing, ensuring that data packets reach the correct destination across different networks. IP Internet Protocol is the backbone of this layer, responsible for delivering packets to the right address. Another important protocol in this layer is the ECMP, Internet Control Message Protocol, which is used for sending error messages and performing network diagnostics such as with the ping command to test connectivity. Finally, we reach the network access layer, which deals with the physical transmission of data. This layer manages how data is physically sent over the network using hardware and communication standard. Ethernet is the standard for wired networks, commonly used in homes and offices for high-speed stable connections, and Wi-Fi, which is the wireless fidelity, is the standard for wireless networks, allowing devices to connect to the internet without cables. There is also PPP, which is point-to-point protocol, which is used for direct connections between two nodes, often in VPNs or dial-up connections. To truly understand how data travels across networks, let's walk through a real-life example of what happens when you access a website like www.example.com. This process perfectly illustrates how data flows through the OSI model, which organizes network communication into 7 distinct layers. When you type the web address into your browser and hit enter, your request travels from the top layer, the application layer, down to the physical layer. It goes through all the layers where it's transmitted over the network to the server. The server then processes that request and sends the response back with the data flowing in reverse order. That means through the physical layer, and it goes up step by step until the application layer, where the website will be displayed on your screen. The process starts at the application layer, layer 7, where user interaction takes place. When you type www.example.com into the browser and press enter, the application, whether it's Chrome, Firefox, or another, initiates the web request using protocols like HTTP or HTTPS. This layer enables application to communicate over the network and handle user-generated requests. Once the request is generated, it moves to the presentation layer, layer 6, where the data is formatted for transmission. If the website uses HTTPS, the data is also encrypted at this stage to ensure secure communication. Next, the data passes through the session layer, layer 5. This layer is responsible for establishing and managing the session between your device and the web server. Think of it as opening a secure communication channel that keeps the connection active while you are browsing the website. After the session is established, the data moves down to the transport layer, layer 4. Here, the data is broken into smaller packets using Transmission Control Protocol, the TCP. TCP ensures that the data will be delivered reliably and in the correct order, adding a mechanism of error detection and retransmission if any packets is lost. The journey continues to the network layer, layer 3, which is responsible for routing the data across network. This layer assigns an IP address to the data package, ensuring they reach the correct destination. The web server hosting the www.example.com. Once the IP address is assigned, the data moves to the data link layer, layer 2. Here's the packaged into frames with the MAC addresses to facilitate local network communication. This ensures the data can be delivered accurately within your local network, such as from your device to your Wi-Fi router. Finally, the data reaches the physical layer, layer 1. At this layer, the data is converted into electrical signals, light pulses, or radio waves, depending on whether you are using Ethernet, fiber optics, or Wi-Fi. These signals physically transmit your web request across the network to the server where www.example.com is hosted. Once the server receives your request, it processes it and prepares the response, which contains the website data. This response flows back through the OSI model in reverse order, starting from the physical layer and moving up. The server transmits the data as raw signals, whether electrical, optical, or wireless, at the physical layer, layer 1. As the data travels through networking equipment, the data link layer 2 ensures the framed correctly using MAC addresses for accurate local delivery to your device. The data then reaches network layer, layer 3, where IP addresses of your device is used to guide the response back through the internet. At the transport layer, layer 4, the data is reassembled from its packets and mechanism ensure that everything has arrived intact and in the correct order. Moving up to session layer, layer 5, the ongoing connection between your device and the server is maintained to support smooth communication. As the data reaches the presentation layer, layer 6, it's decrypted if HTTPS is used and converted into format that your application can understand. Finally, at the application layer, layer 7, the browser processes the data and displays the website on your screen. This is the part you actually see the final content ready for the interaction. When you request a website, your data flows through the OSI model layers twice, once as a request and then it goes back in the reverse order as a response. Exploring how data moves across networks, it's important to understand the role of content delivery networks, CDNs. A CDN is a system of distributed servers strategically placed across different geographical regions, all working together to deliver content like websites, videos, images, and scripts, quickly and efficiently to users around the world. In today's digital landscape where speed and performance are critical, CDNs play a vital role in enhancing the user experience. So how does a CDN work? When you request content online, such as opening a website, that request doesn't always travel directly to the website original server, which could be located halfway across the world. Like, for example, you will be in Asia and the website's original server will be in the US. So instead, the CDN redirects your request to the nearest server, known as an edge server. This reduces the distance that data needs to travel, leading to faster load times and lower latency. Essentially, instead of your data making a long journey across continents, it takes the shortest, fastest route to reach you. CDNs offer several key benefits that improve both performance and security. First, there is speed. Since content is delivered from server that's geographically close to the user, websites and applications load much faster. Next is reliability. CDNs are designed to handle a large amount of traffic without crashing, even during peak times like flash sales or viral events. They also enhance security by protecting against threats like DDoS attacks. By distributing traffic across multiple servers, CDN can absorb and mitigate those attacks more effectively. Lastly, CDNs offer scalability, making it easy for businesses to handle traffic spikes without any performance issues, such as during major product launches or global events, like, for example, Black Fridays, where, the e-commerce websites, they start having a lot of traffic, more than usual. So the CDNs here is such a great solution to manage that. To put it in simple terms, imagine a global pizza chain. Instead of shipping a pizza all the way from Italy to New York every time someone's ordered the chain. Now, let's talk about load balancer. What is a load balancer? Load balancers are smart traffic cap for servers. It efficiently distributes incoming network traffic across multiple servers to ensure that no single servers get overwhelmed. This not only keeps website and application running smoothly, but also enhances performance, availability, and reliability. So how does a load balancer work? When users send requests to a website or an application, whether it's loading web pages, submitting a form, or streaming content, those requests don't go directly to just one server. Instead, they first reach the load balancer. The load balancer then analyzes the current load on all available servers and determines which one is least busy or performing best. It forwards the request to that specific server to handle the task. If a server happens to fail or go offline, the load balancer automatically redirects the traffic to healthy servers through a process known as a failover, ensuring that users don't experience downtime. There are different types of load balancers based on how they are deployed. Hardware load balancers are physical devices designed to manage network traffic, but they are becoming less common due to the rise of more flexible software-based solutions. These solutions can be easily integrated into cloud environment, offering scalability and cost effectiveness without the need for specialized hardware. The benefit of using a load balancer are significant. First, it ensures high availability, meaning if one server fails, the traffic is seamlessly routed to another functioning server, minimizing the downtime. Load balancers also support scalability, allowing businesses to handle increasing amount of traffic without compromising performance. Additionally, they contribute to optimized performance by reducing servers' response times and preventing any single server from becoming bottleneck, which leads to a faster load times and a better user experience. To put this into perspective, imagine a toll booth with multiple lanes. A load balancer functions like the person directing cars to the least crowded lanes to keep traffic flowing smoothly. Now, let's summarize this. Load balancer is a critical tool for managing traffic across servers, ensuring high availability, scalability, and optimized performance for websites and applications. It's the hidden force that keeps online services running efficiently, even when users' demand spikes or technical issues arise. Since this course is more directed to project managers or scrum masters and people working with software development teams, I wanted to add this section just to give you some examples of issues or complaints that can be reported by developers, and the root cause might be related to network. Not all the time. I'm giving just random examples so you can understand and you can link what you study today to the real life and the practice that you have with your team. So let's start with the first example. One of the developers in the team will come up in the daily and they'll be like, oh, I couldn't connect to the database server. And this issue might be related or due to the firewall blocking the database port. For example, if you are using MySQL, it typically operates on port 3306, I believe. If the firewall setting prevents traffic through this port, the connection fails. So the solution usually involves checking the firewall rules and ensuring the necessary port is open. And this can be done by the team themselves if they have the hand over, changing the firewalls and so on. And if you have a dedicated network team, they need to be involved. Also, if you have, for example, an e-commerce website and some people from a certain and specific location, they raise an incident that they are unable to connect to the website only in that region, that will make you think, oh, this is probably a CDN issue, So this is how you can link the knowledge that you gain today with, the common issues or the things and the incidents that you will face in the future. It will help you troubleshoot. It will help you, think properly and bring, this technical knowledge and technical terminology to make everyone see that you also understand what they are talking about. All right, so we reached the end of our course. I hope it was useful and helpful to all of you. Make sure that you like the video and subscribe to the channel. If you have any recommendation or any request, or if you have a feedback, you can leave it in a comment below, or you can reach out to me through my social media accounts in the description box. Thank you all, and I wish you all the best. Bye!